Welcome to this special edition of one of my videos for my channel here. This was specially created for the International Group for Mathematical Creativity and Giftedness. And so if you're a regular part of my audience coming across this video, I've actually already filmed a solution to it. However, I wanted to recreate that solution process and speaking to a specific audience, namely the one that came from the March 2023 newsletter, problem number 20, and this is the Problem Corner solution. So the source of the problem was the 2021 Fall American Mathematics Competition, 10A, which is for grades 10 and below, approximately 16 and under. Problem number 23. If you're unfamiliar with this competition, it is the one that leads in a series of competitions that ultimately culminate in the formation of our International Mathematics Olympiad team. The AMC is the first leg for most people in that journey of getting to that level. And so this problem, as I mentioned in the newsletter, I really like it because students who may not have training of high-level ideas and concepts could easily become kind of demoralized right here. Like 16 and under, it's rare that you see things that look like this in your homework unless you're at a particularly specialized school or you've come across it through your own endeavors. And so I like that. I like that even though you feel this massive discomfort at about this point in the problem, that the student who says, you know, I don't really know what I'm doing, but I'm not going to give up. I'm going to go ahead and take a few steps and proceed further and just kind of see what happens, right? That's what else, what could go wrong? Nothing, really. Just spend the time and see what occurs. And so as I mentioned in there, I call this concept, this is my personal name for it. I'm sure there's some official name where other people have quantified this idea in a technical terminology. I simply call it the deserted island principle. And so I discussed that in there and I explain it, but for the audience who maybe did not come from the newsletter, the deserted island principle is as such. If you find that you've been shipwrecked on an island, it's deserted, right? Hence the deserted island principle, and you don't know what to do to survive. You've never had any outdoors training. You don't know how to start a fire. You don't know how to spear hunt, forage for berries, roots, anything that you could do. You don't have that training. So your options are lay on the beach. In the sand, you write SOS somewhere above where the shoreline would come up for the tide. And SOS is a send for help, of course. And maybe you hope that some form of humanity, a helicopter comes by or a plane or some kind of boat, and you can wave a palm frond at it and hope to survive, right? But barring humanity and one of these vehicles comes by to save you, barring something like that happening, you're going to have to survive at least probably a few days. And as it gets dark out and there's no heat, you might realize I'm going to need to start trying to generate some form of sustenance and some form of heat in order to survive. And so you're going to go out and you're going to start sharpening sticks, and you better do it quick because the longer you're there, your energy level is depleting, and it's better to search now while you have your full wits about you, right? And so you're going to go out, sharpen a stick, you're going to be hunting out there for something that you could maybe eat, and you'd probably even eat it raw at some point, even if you couldn't get the fire going, but you're going to do things like that. You're going to dig up some roots and decide, this looks like maybe it could give me some kind of nutrients, and you will eat that and attempt to live that way. Berries, all of that kind of thing. And so because of that, that's why I call it the deserted island principle. It's the will to survive even though you don't know how. And that's exactly what you have to have in a problem like this when you come from that perspective. Let's get started in discussing what that would look like to this student. So for each positive integer n, let f sub 1 of n be twice. So a lot of times too, I like to teach to interpret as you go. Makes sense. Don't keep reading. You don't know what you just read most of the time. There are times I will skip over a difficult to understand passage and return to it. But these kinds of things, I want a positive integer n, and for each one, then I'm just going to say, well, I don't know, let's let n equal 1 and see what this means. Let f sub 1, then if that happens, f sub 1 of 1, it will be twice the number of positive integer divisors of 1. Well, 1 only has one divisor, and so twice that, it would come out to be 2. Okay, that wasn't so bad, and you feel more comfortable, and because you feel more comfortable, it might allow you to get past this part here, which is the most difficult part of it to read and process. And for j greater than or equal to 2, but where does it cap? Where's the upper end of j? Apparently there is none, and we'll have to figure out how we're going to navigate that when the time reveals it to us by proceeding. So let f sub j of n, so now I've got two unknown values working together, don't know what to do with that, equals f sub 1 of f sub j minus 1 of n. Okay, that's weird for a lot of students. They don't know what to do. It's at this point that a lot of students go, I can't do this, and they just skip. And that's why if you look at the statistics on the MAA website, you will see that 70 some odd % of students actually skipped this problem. They omitted it. They probably ran out of time before they got to it, but sometimes students will look ahead, they'll go, oh, I can't do that one, can't do that one. Okay, and then they'll go back to an earlier one that they skipped. So of the students who answered it, I think about 4% got it right around there. So let's keep going. For how many values of n less than or equal to 50 is f sub 50 of n equal to 12? And again, at this point, you're just kind of confused. You don't know how to proceed. You fear. You don't think, I can't do this. You lack confidence. And I really like the student who doesn't accept that position for themselves. They don't stay there. They don't say, you're right, I can't do this, and they give up. If they can overcome that and they can proceed past and just start playing a game of what if I do this, what if I do that, and they experiment. They try to see what happens when they take certain actions or certain values are chosen for j or n. And that's the best part. When they start to go a little ways around the bend, I think of it like a metaphor or analogy that the item writers of the competitions like to obscure the solution path. They like to make it look dark and ominous, and then it's like, oh, I can't get past. It's all a jungle there, and I don't know how. And they want that feeling. They want you to feel that, and then they want you to persevere beyond it. And the student who goes around that bend oftentimes will find the path opens wide up, and they can see exactly what's going on. They just have to move a few steps and get started. And as I noted in there, such as it is true in problems, such as it is true in life, let's continue with this process then in regards to that. So it says j greater than or equal to 2. If I'm that student, I just say, well, let's just start at j equals 2. Okay, all right, I don't feel comfortable. I'll say j equals 2. I'll keep the n as 1. That's going to give f sub j2. That's going to be 2 of 1. And what does this equal? It's got a 1 here, so I copy 1 down. J minus 1, I guess I just subtract. So 2 minus 1 is 1. F sub 1, n we still have as 1. And we say, okay, well, oh, that looks familiar. I've got that. It's 2. So this must be f sub 1 of 2. And that is this thing. And that's just twice the number of positive integer divisors. Oh, 2 is prime, has 2 divisors, of course. And so 2 times 2 is 4. Okay, you made it a little bit farther. That's like your first, maybe second step, if you count this as the first step, into that dark and ominous path. And you just keep going. And you say, okay, well, I guess we could increase j by 1. We did that one. We'll just leave n alone for now. And so we're going to say, what if j equals 3? And we get f sub 3 of 1 is going to equal f sub 1. It's always f sub 1 here. That's a constant. And then the j minus 1, well, j is 3. If I take away 1, I get 2. I'm going to get f sub 2 of 1. And that, again, is right here. We've seen that. We created that ourselves. And so we get the 4, not the 4. You have the 4 in there. So it's going to be f sub 2 of 4. No, I'm sorry. Yeah, f sub 2 of 4. Yeah, that's it. Wait. Okay, there we go. I know the mistake. Okay, so then, sorry, I lost train of thought. So it's this f sub 1, and then the f sub 2 of 1, this expression is 4, so you get the 4 there. And then we continue to proceed. How many divisors does 4 have? 1, 2, and 4, that's 3. I double it to get 6. And so here we go. Sorry, I'll try to slow down my speech. I understand that there's not always native English speakers who watch this, and maybe the fast speaking is difficult to follow sometimes. So let's continue on. Again, we don't quite feel comfort, but we do start to notice a pattern. We start to say 2, 4, 6, is it going to be 8? Maybe we're just adding 2. Maybe it's just evens. Don't know. And you keep going, and you say f sub 4 of 1. J is 4 now, so then this is always a 1 here. We should have noticed as we're going, once you start laying down a few of these steps, the tracks becomes more familiar. This j value, the j minus 1 value actually, is always increasing by 1 in our current iteration of this process. So we're going to get f sub 3 of 1, and that's going to be what we have here, and that was 6. So again, we keep this 1, we swap out the entire inside for the number 6, and 6 has 1, 2, 3, and 6. 4 divisors times 2 is 8. Now, this is one potential for a mistake here. People might just think, oh, it's just the evens. And they conclude that, and they stick with that conclusion. Don't do that. You want to keep going a little bit farther. If we do f sub 5 of 1, one more level of this, you're going to get f sub 1 of f sub 4 of 1. And that's going to be what we have here, which is 8. And now I have f sub 1 of 8. And wait a minute, 8's got 1, 2, 4, and 8. That's 4 divisors. It's going to double to 8. And right here is that first aha moment. It's where you really get the first break in the problem, and you go, wait a minute, then they're all going to be 8 after this point. That's significant. That's a significant conclusion, I call it. And so once you find that significant conclusion, then okay, now we can start trying to think about what might be going on here. We've seen enough examples, okay? We want f sub 50, so this number to be 50 of n, where n is less than or equal to 50, to be 12. Well, if I get 12 as my output of this function, then there must have been 6 divisors. Huh. So if there's 6 divisors, maybe we should think about numbers that have 6 divisors. And what would happen is once you hit that 12, now I'm curious, what would happen if I got 12 in here? So what if I had f sub 1 of 12? Okay, well f sub 1 of 12, 12 has got, I'm just going to list them, right? 12 and 1, 6 and 2, 4 and 3. Well, that's 6 divisors. That's going to produce a 12 again. So just like this was always the 8, let me erase that so you can see it a little bit more clear. So this is going to come out to be 12. And so since this was an 8, and it repeats to 8, and it repeats to 8, and it repeats all the way, it would go all the way to f sub 50 of that value would end up always being 8. So it's going to chain after a while and be constant. Well then, since this f sub 1 of 12 produces 12, it will always produce 12. So if we can find any way to hit the number 12 as an output, then the remaining outputs will all be 12, even up until you hit f sub 50 of 12. Okay, well then based on that reasoning, we're looking for things that have 6 divisors. And so we're going to go to our knowledge of how many divisors an integer would have, and it's based on the prime factorization. And so we say, well, if I do p squared times q squared, these are prime numbers, mind you, if my input value was equal to that, then I would have 2 plus 1 is 3, and 3 here as well. Why is it this? I'll just explain it. I'm sure all of this audience knows, but because you're making a choice, it's fundamental counting principle, we call it. You're choosing between p to the 0, p to the first, and p to the second, and q to the 0, q to the first, and q to the second. You have 3 choices times 3 choices. Even though your exponent is 2, you have to count the 0 option, and so you have 3 choices times 3 choices. That's going to give you 9. We don't actually want that. We actually, I'm thinking of plus, we actually want q to the first. So we're going to have this set up. So p to the second times q to the first, that's going to be 6 divisors, 3 times 2, right? So 3 times 2 would be 6. Okay, then what could p and q be? Well, I start with the smallest primes. I mean, we got to have n be less than 50. We can't have too many options. So let's just pick that p, the most powerful one on the board because it's squared, is a 2. If I do 2 squared times 3 to the first, we already know that one. It's 12. We have it right here. So we know that's good. Then what if I do 2 squared times 5 and 2 squared times 7? And what about 2 squared times 11? That's 4 times 11 is 44, and 4 times 13, the next prime, is 52, which is too big. So we know that we have all of these, this type here. We could also do 3, put 3 in this p-value spot. And so we're going to say if we had 3 squared times 2 to the first. Well, that's 9 times 2 is 18. That's fine. What about 3 squared times 5? 3 squared times 5 is 45, of course. And so let's make a list of these, right? Let's keep track of what we're finding. We've got 12. We know that's good. I'm going to go to this 18 next. And then I'm going to go to 20, which is the 2 squared times 5. And again, this is that point in the problem where the student is starting to really pick up their confidence. They see it. I can do this. I can make this happen. And the rest is, there is a trap coming up. Maybe you found that trap too when you solve this problem. We'll talk about that as we proceed. But let's see. 4 times 7 is 28. So we're going to have 28 here. And then the next one we're going to have is 4 times 11 is 44. And the next one is 9 times 5 is 45. And so now what? We continue and try to find one more. 9 times 7 is too big. I mean, you're already at 45. It should be logical. You're going to go over your cap of 50, and we don't want that one. So then we say, well, what about 5 squared? And many students did not think of the 5 squared on the test. They didn't think to check that one, and they likewise found their trap answer for them. They just said, well, 5 squared is already 20. It's not going to work. But you have to check it. You have to check because our brains are fallible. And as much as we draw these conclusions in our mind quickly, because we're fairly smart and able to do that, fairly capable, then we say, that conclusion I drew that's correct. And that's something else the students also, when taking these tests, have to overcome. Their pride, their hubris, if you will, that they're not willing to second guess themselves. And they should be. And then there's also the case of there's too much second guessing, and that causes also people to skip questions that they knew what they were doing. That's why we want to be able to conclude definitively, yes or no, does this work? And so we just check. We could say, 5 squared is not going to work, but let's check. So we call that oftentimes trust, but verify. So if I say 5 squared, what could go here could be the 2. And that gives, well, that's exactly 50. Well, that's pretty good, actually. That actually is in our realm here, okay? And we'll talk about if these actually work in a second, okay? We'll come back to that. But there's still something else we haven't done to get 6 divisors. Another way that you could get 6 divisors is if you had the prime to the 5th power. And in such a situation, you would just add 1, you would have 6 divisors. So if I put a 2 here, 32 has 6 divisors, of course. 1 and 32, 2 and 16, 4 and 8, that's 6 divisors. So then this would also work, and you'd have to put the number 32 in here. What about 3 to the 5th? Way too big, right? Don't need to worry about that. And there's no other way to get 6 divisors. It's either 6 times 1 itself, right? Or 3 times 2. So because of that, we're pretty sure we've exhausted this type here. And so we get 8, and this was the number 1 trap answer for those who answered it. Again, there was like about 25% of students, or 20 some odd percent, did attempt the question. The number 1 answer was the 8. It was only slightly higher, like 5.8%, something like that, had answered with this, and it's not the correct answer, as we've already mentioned. So the question would be, let's say you didn't know that, right? And you got to this point. This is where you have to go, okay, I felt really comfortable, but now I have to start checking my thinking and my conclusions that I drew, the inferences that I made. I'm drawing an inference that this is the end of the list because these are all the things that produce 6. But what we have to do is step out one more level and think, what about if I had a number n that p sub 1 of something gave me one of these? Well, we already know that if it gave us 12, we would always get 12, so we don't have to think about that. But what about the 18? Is there any number that has 9 divisors that we could use? Well, I mean, the smallest one would be 2 to the 8th probably, or is that the smallest? If we had the 9 divisors, that was the mistake I started with at the beginning when the q was 2, then I could just say p squared times q squared. Oh, if I chose 2 and 3, we get 36. So think about it. Make sure we're right. We got to check our thinking. We say p sub 1 of 36. Well, 36 would have 9 divisors, so I would double that and get 18. And if 18 was here and I did the next chain, right? This chain action is going on. You increase your j value wherever you were at by 1, then where would I end up at? Well, we already know. The next one up, the p sub 1 of the next j value would be with an 18 in here. And that, of course, would give you 12. And from there, you would chain the 12s until the very end. Oh, wow. So because of that, we then have to say there is the value of 36 added to this list. And so you say, okay, we've got 36. That puts us here at 9. Are we missing any others? So now we have to think, where could we get another solution of this type? Is there anything else in here? What about 2 squared times 5? That's 100. That's not going to be it. Obviously, 3 times 5 would be larger. So 3 squared times 5 squared. Then we have to think what else we could try. What about the other ones over here? What about the 20? Could I have 10 divisors? And it would be at this point that if the student is thinking about this, why don't we just go ahead and cut all of these in half? So if I cut all of these in half, we're going to have the 18 would give 9, the 20 would give 10, the 28 would give 14. We don't check 12 because we already know it's the 6. The 44 would give 22. And then you're going to have, you can't cut that in half. The 50 cut in half would be 25. The 32 cut in half would be 16 divisors. Okay? So this would be the number of divisors that we would need, because when we do twice the number of divisors, we would then arrive at one of these values, which then produces the 12, and the 12s will chain just like the 8s. So then we've done the 9. Hopefully we finished that one off. 2 to the 8th is going to be 256, so too big. We checked this one. There aren't any other ways to get 9. So we go to the 10. How would I do that? What if I did p to the 4th times q to the 1st? So I've got p to the 4th times q to the 1st. If I add 1, 5 times 2 is 10. Okay, let's find the primes. 2 to the 4th is 16 times 3, 48, less than or equal to 50. So 48 is another acceptable value. I'll put it in front of the 12 here. Actually, I probably should put it to be more less. My OCD is kicking in. I will put it here as well. Okay, so 48 would work. Just double check it. If I check 48, what are the divisors? It's this. We get 10 divisors. Then what is p sub 1 of that? 10 divisors becomes 20, right? When you do the number of divisors as 10, you double it to get this 20 here, and then that 20 produces the 12, and again, we chain. So what else? What about the 14? The 14, you'd have to have, p to the, 6th times q to the 1st. 7 times 2 being 14, but 2 to the 6th is already 64. So even with the smallest possible prime chosen in this value, you don't get it. So that's not going to work. And you continue checking all of these. The 22, you have to have 11 divisors, not going to get there. Actually, these are the number of divisors. So you'd have to have 22 divisors. So again, it'd be similar to this, but you'd have p to the 10th times q to the 1st to get 22 divisors. Not going to work. Same problem for 25. You'd have to have p to the 4th times q to the 4th. And that's already, let's look at that real quick. Let's make sure, right? Don't make assumptions that we don't kind of verify. 16 times 81, yeah, going to be a little bit over 50. The 16, we want 16 divisors. You could do, what about, p squared times 16 divisors? Maybe we could do this. What about p to the 1st times q to the 1st times r to the 1st times s to the 1st? That would be 2 times 2 times 2. That would give 16 divisors and let us produce this 32. If I do 2 times 3 times 5, you're already at 30. times 7, you're over. Feel pretty comfortable, we can't get any more, and that is going to be the final answer to the question. So again, I hope that those of you who came from here and you solved this problem, that you did second guess yourself at that point and dodge the trap. And to be honest, many experienced people, including, I kind of made that mistake. If you go back and watch my original solution to this video, I wasn't really solving it with the mindset of I have to get this right like on a contest. I was just solving it and I thought, oh, so is it 8? Because I got to move on with my life. But maybe you felt the same way. Maybe you got this and discovered later that now the answer is actually 10. Don't feel bad. Many of us, this test is very crafty. The item writers for it are very intelligent individuals who are good at identifying things that will fool people. But it was getting to this point here when the student really takes off. And then if they can dodge the trap and arrive at the 10, very satisfying problem. I really hope you enjoyed it. Thank you for watching. I hope to see you in the next newsletter's Problem Corner. You have a wonderful day.